right, well, I'm absolutely delighted to be able to join by Zoom. It's always wonderful to be able to come to PHENO in person, but this is great fun. I'm going to be talking about some new thoughts on the hierarchy problem. I'm not going to be talking about philosophy at all in this talk. Of course, it's amusing to talk about the philosophy of the hierarchy problem. Is it a problem? Blah blah blah. It's good for like a lunchtime discussion, but the issues are pretty trivial, and I don't want to talk about them here. So I want to talk about some new ideas about the hierarchy problem that developed at various levels. Let me begin by saying that at least my own personal best bet for what's going on, given the sort of widespread surprise of the absence of natural new physics at the LHC. My own best bet is actually what I've thought for already 5 or 6 years before the LHC, since the mid-2000s, that what's going on at the TeV scale is something like close to minimal split SUSY. I remind you, when we first started talking about this a long time ago, it was a heresy to say the word supersymmetry and fine-tuning in the same sentence, because even a minimal split SUSY involves scalars at hundreds or thousands of TeV in supersymmetry, and so a fine-tuning of around a part in 10,000 or a part in a million for electroweak symmetry breaking. Of course, that's to be compared with the usual tuning of at least a part in 10 to the 90 in typical supersymmetric theories for the cosmological constant. So, so that's small potatoes compared to the CC. The point of having any light states in minimal split SUSY is to have the very simplest picture of WIMP dark matter work. And I also want to remind most of you that the absolute simplest picture of WIMP dark matter, where we have an electroweak doublet or triplet, is alive and well. It's the Baroque WIMP models that are excluded experimentally, but the very simplest ones are alive and well, where the light states could be between 1 and 3 TeV. They're not made at the LHC, and for good reasons, very small direct detection cross sections. The basic picture of minimal split SUSY made a mild but correct prediction for the Higgs mass between 120 and 135 GeV. The gluino might still be accessible at the LHC, it's not inconsistent, but certainly both the electroweakinos, the dark sector, the dark stuff, as well as the gluino, must be seen at 100 TeV collider if this picture is correct. And as Matt was reminding us earlier today, EDM searches are really a spectacular window into physics up at even 100 or 1,000 TeV indirectly now. Those are absolutely incredible experiments. So that's my own personal picture. If you woke me up in the middle of the night and asked what I think is going on, this is what I think is going on. But it's definitely worth thinking about alternative ideas, alternatives to the sort of 40-year paradigm that we had been exploring. And so that's what I want to talk about today, sort of two topics. The first one is sort of qualitative comments and a few toy examples. There might be something deep in it. There might not be. But anyway, the set of ideas revolve around the sort of famous connection between the UV and the IR that we expect to have whenever there's gravity in the world, the possibility of hidden symmetries that we've missed, of which there really are. And I'll tell you about some of these hidden symmetries. It's not clear they'd be related to the hierarchy problem, but there really are hidden symmetries that we didn't know about 10 or 15 years ago in quantum field theory, as well as the sort of mechanism of what Yuval Grossman and I are calling tuning and transcendentality. So that's one topic. That's, as I said, somewhat more speculative. The second topic is ongoing work with Rafael Dagnolo and Hyung-Do Kim about the general idea of the weak scale as a trigger. As you'll see, the first idea is some sort of qualitative experimental signals. The second one has extremely precise phenomenology. It's sort of surprising that it's not excluded already. And there's nothing we can do about it to decouple these signals. So these two ideas are quite different from each other. They're also different in the kind of experimental signals that you would be talking about. All right, so let me just very quickly put our discussion in context. The last sort of 400 years have been the march of reduction in fundamental physics, have been the march of reductionism and the march of symmetries. But we have lots of indications in the 21st century that we really need really big new ideas that go beyond the paradigms of space-time and internal symmetries. We have the indications that space-time is an approximate notion. We have indications, related indications from gravity of basically the end of the reductionist paradigm. The reductionist paradigm is fundamentally wrong. We don't understand the questions like, why is the universe big with big things in it, which is the avatar of the hierarchy and the cosmological constant and hierarchy problems. So I think these problems might be related, and they indicate really new ideas are needed beyond the paradigms of space-time and internal symmetry. So let's remind ourselves in the context of the hierarchy problem what the sort of fundamentals of the problem is. We have a very good understanding of why a particle like the photon is massless, because the number of massless and massive, because the number of degrees of freedom of a spin 1 particle changes discontinuously when you go from being massless to massive. 2 is not equal to 3, and so the masslessness of a spin 1 particle is robust against any perturbation. And this is also why gauge fields and chiral fermions can be easily engineered in condensed matter systems. The difficulty with the Higgs is that it has no degrees of freedom. And so the number of degrees of freedom does not change discontinuously as you go from massless to massive. And that's why we don't understand why the Higgs isn't enormously more massive. Why isn't dragged up to the highest ultraviolet scales that we know? And I talk about it like this just to emphasize that it's really special. The Higgs is really special. Its simplicity is what makes it so perplexing. The fact that it has it's spin 0, there's no charge, there's no quantum numbers at all other than its mass. And this also explains, this argument also explains why we don't naturally see something like the Higgs arise in condensed matter systems, even though we can have things like chiral fermions and gauge fields emerge as robust long distance excitations in condensed matter systems. So both the problem of the cosmological constant and the problem and the hierarchy problem are then related to this sort of failure of symmetries to capture an important feature of the crucial feature of the macroscopic physics of our world. As we said, in the case of the Higgs, we have 1 degree of freedom whether the Higgs mass squared is positive or negative. There's no difference. That's the hierarchy problem. That's basically the same story as the cosmological constant. We have the same amount of symmetry. The number of generators doesn't change when we go from positive to 0 to negative cosmological constant. So symmetries are not enough to control this. All right, so we're clearly missing something huge about the quantum mechanics of our relativistic vacuum. And I want to emphasize that the discovery of the Higgs is crucial for this, because it already indicates that our relativistic vacuum is qualitatively different than anything we've seen anywhere else in physics, anywhere else in condensed matter physics, for example, not just at the Planck scale, but already here, right above our head at the SEV scale. All right. So that's for context. Now let's talk about the first set of ideas revolving around these words: UVIR, hidden symmetries, and transcendental tuning. Okay, so let me. So the story of UVIR is, I think, by now a familiar one. We've known for decades now. There's something new about gravity. As we go to very high energy scattering ceases to probe short distances, because when the energies become much larger than the Planck scale, you make a large black hole instead. And so you can't see what's going on at short distances anymore. Relatedly, that's why we don't think we can talk about the notions of space-time at Planckian distances either. Importantly, this means that the reductionist and Wilsonian effective field theory paradigm are fundamentally false, ultimately, when we get to the Planck scales. It's not true that the physics is given to us at arbitrarily short distances, and then we just have to see what happens at longer distances. There is no such thing as arbitrarily short distances, and arbitrarily high energy starts turning into very large distances again. So this says at a fundamental level, the laws of nature are, again, nothing like what motivated the Wilsonian paradigm to begin with, which is the analogy with condensed matter physics. There's something deeper and more radical going on. But you might think that if something like this is going on, it's only going on near the Planck scale and be irrelevant for the practical aspects of life down here near the weak scale. And that might be wrong. But before talking about anything in more detail, I just want to make the following qualitative point that we'll come back to again and again. It's crucial to experimentally probe not only the on-shell Lorentzian properties of the Higgs by producing the Higgs and having it decay, but also its off-shell properties. In other words, how the Higgs couples the things in loops. Now, in ordinary effective field theory, in ordinary quantum field theory, in the Wilsonian paradigm, these things are continuously related to each other. In fact, the standard way of thinking about quantum field theory, the Wilsonian way of thinking about quantum field theory, is fundamentally Euclidean, and we get to Lorentzian physics by analytic continuation. But I want to stress that this whole picture of the UVIR connection in gravity can change this expectation. And it can change it in a way that gives you sort of order 100% differences between naive effective field theory naive quote-unquote effective field theory calculations and the right answer. Now, for this, I just want to give a couple of toy examples. Toy example one is the following. Imagine an experimentalist has measured some quantity, F experimentalist of T, F experimental of T, some variable T that is units of time, and they've measured it for positive time, and the time much bigger than some UV scale TUV, and they discovered there's a very good fit. It looks like 1/T. Now, an effective field theorist would look at say, oh, okay, great. I know that F experimental of T is 1/T. And in particular, I'm so smart, I know that there has to be some kind of singularity near T equals 0. And I can actually make a reliable effective field theory, where effective field theory means here at times much bigger than TUV. I can make a reliable calculation where I do a big contour integral of F around this whole contour, and I get 1. Okay? Because F of T goes like T. So that seems totally reliable. It doesn't seem to need anything what's going on near the origin. However, remember, the experimentalist has only measured this on the real axis. The effective field theorist, in their mind, is continuing it everywhere here, but staying away from the origin and thinking that things are safe. And this extrapolation can be completely wrong. For example, the actual function could look like 1 minus 10 to the minus 120 T over TUV divided by T. And you'll notice that this has a property that on the real axis for positive time, it's exponentially close to what the experimentalist has measured. But you'll notice that this function has no singularities at all, no poles at all, no singularities of any sort inside the circle. And so this contour integral, instead of being 1, is 0. It's discontinuously different. Now, this might seem like some abstruse fact, but in fact, it's a crucial mechanism in the context, for example, of the ADS-CFT correspondence, for telling us how the bulk of the space-time does not exist precisely. Singularities that you would attribute to the existence of sharp bulk points are actually removed in the boundary theory by essentially exactly this mechanism. I can give another explanation for where this comes from. You see, as a theorist, you might say this function 1/T is coming from some integral over energy, e to the I energy T. And so the pole at T equals 0 is coming from the ultraviolet as the energy goes to infinity. Okay, well, you might say, well, maybe something new is happening at high energies. Maybe there's some damping of this function that goes like a power. And the power at high energies is what you would expect in some kind of field theoretic behavior. If you have the power, then this integral no longer necessarily has a pole at T equals 0, but it's still some kind of branch cut at T equals 0, because the convergence of this integral depends crucially on the sign of the imaginary part of T. So if T had the wrong imaginary sign, this integral would blow up. And so there has to be some kind of singularity at T goes to 0. And relatedly, this big contour integral out here is always going to give you 1. But if the behavior at high energy actually beats the exponential, if it's like Gaussian like that, for example, which is what you expect in a gravitational theory, broadly speaking, then the sign the time here is utterly irrelevant for the convergence of this integral. There's no singularities in here at all. And so this contour integral goes from being 1 to 0. So you see, by changing the expectation of what happens arbitrarily far away, lambda can be as far away as you want, you make an order 100% change to something that otherwise naively seems like a reliable effective field theory calculation. And where is the mistake? The mistake is in continuing the Lorentzian answer that the experimentalists got for positive time and assuming that you could analytically continue it everywhere. That's what we do in ordinary Euclidean quantum field theory. It's correct in local quantum field theory. it's wrong in gravity. And this is at least a toy example where you see the wrongness is not restricted to something that only shows up at very high energies. The wrongness can make a 100% difference to what appears to be a reliable, quote-unquote, effective field theory calculation. So again, I repeat that just quite model independently, it's crucial to probe Euclidean off-shell properties of the Higgs, because these are probing exactly this continuation that we ordinarily take for granted. So for instance, we might imagine that there's something that's not ordinary compositeness, but that's making the Higgs and the tops mutually non-local when the tops get off-shell by more than a few hundred GeV. That would shut off the famous top loop UV sensitivity. But what would it do? It would give a 3% modification to Higgs to gamma gamma, or maybe a 10% modification to Higgs to glue glue. That's the size of the effect that you would think if this loop is shut off at let's say 500 GeV. And this is the sort of modification you could look for. It's perfect for a Higgs factory. Similarly, you could see whether radiating off a Higgs at large PT is suppressed, again, because these couplings would be shutting off when the top quarks get off shell by more than a few hundred GeV. And this is very, very hard to look for, this effect of the shutoff of this cross-section for large Higgs PTs. It's hard to look for at the LHC, but it's perfect for 100 TeV for life. All right, so that's a qualitative comment. I have 10 minutes, I think, right, Raman? Hello? Oops. Okay, sorry. Let me keep going. Okay.
Yes, Nima. 15 more minutes.
Okay, great. Okay, good. So let me go to the next couple of topics. Having to do with the idea of hidden symmetries. I'll go over this very, very rapidly. Over the last 10 or 15 years, in the study of scattering amplitudes in gauge theories, gravity, more recently totally non-supersymmetric general theories like phi cube theory, one general attitude has been to try to understand. We ordinarily think about amplitudes as arising from local and unitary evolution in space-time. Picture of Feynman diagram, that's the standard way we think about things. But they have so many interesting hidden properties that it's sort of clear that they're the answer to a different question as well, which does not involve the ideas of space-time and quantum mechanics. And if we understand those questions well, we might have some deeper understanding for where space-time and quantum mechanics come from. Over the past, really the past 8 years, a lot more in the past couple of years, we've been seeing that these more abstract, different sets of ideas have the following character. If you give me the momenta and helicities of the particles that are scattering, instead of imagining that they're scattering in some interesting way in space-time with a wave function evolving in Hilbert space, you associate these amplitudes with a certain kind of object, a generalized notion of a volume that's attached to some abstract spaces. These spaces are called amplituhedra for the case of gluons, or maximally supersymmetric scattering amplitudes at the loop level. And over the past couple of years, we've been seeing in a totally different setting, just scalar theories in any number of dimensions, no supersymmetry, nothing. And they're associated with objects known as associahedra or generalized associahedra. Now, I could talk about this subject for a long time, and actually on Friday I'm giving a 4-hour set of introductory lectures about the recent developments in these things, where some of the things I'm saying on the slide will be the focus of those of that discussion. But one important point is that this is a representation of these simple physical observables that does not obviously look like physics. There's no obvious space-time, there's no Hilbert space, there are these more abstract ideas. But these more abstract ideas, however, manifest some symmetries that are completely hidden in the ordinary Lagrangian. They're totally hidden in the Feynman diagrams, and they're associated with surprising cancellations, literally surprising cancellations at infinite momentum. In the case of gluons, the symmetry is known as dual conformal invariance. there's something that we're calling projective invariant for the case of the simple colored phi cube theory. But the point being, there's a way of representing these physical observables in a way where they don't look like ordinary local space-time quantum mechanical physics, but other things are made manifest. And then there's some way of representing these volumes, some way of breaking up these shapes into pieces that turns into things that look like Feynman diagrams, but that hides the symmetry. So just that fact, and that's just a fact that's been seen in these examples, that motivates a speculation that there might be some kind of dual formulation of physics that represents physical amplitudes, other observables, as associated with abstract geometries in this way. And it could be that in this formulation, it's obvious that things like the cosmological constant and the Higgs mass are exponentially small. But in this formulation, it's not obvious that they're local physics. Another triangulation or another representation, which does make it look like local physics, will, however, make it look fine-tuned. So that's the qualitative idea. That's a qualitative speculation, is that what could explain the tuning is that there's a second formulation where it's obviously not tuned, but it doesn't obviously look like local unitary physics. When you make it look like local unitary physics, it looks consistent, but it only appears to be fine-tuned. That's the idea that we want to explore. Okay, so, and here's a concrete toy model for it, this idea of transcendental tuning. So the concrete toy model is the following. Let's go back to asking a very simple question, like how do we explain to graduate students what we mean by UV sensitivity when we talk about the hierarchy problem? We say, for example, let's say there's some massive new states coupled to the Higgs. If I look at the one loop Kalman-Weinberg potential, there's a piece that I get from the top loop. There's a piece that I get from this massive guy, and it's completely calculable. This part is totally calculable. It comes from it has a logarithm in it. It's totally calculable, but it has an ultraviolet sensitivity to the mass of this guy when I expand it. So one way of describing what we think of as a problem is, of course, I could take this piece and I could add some polynomial terms to cancel against it. But that looks like a terrible conspiracy. This piece has a logarithm, it's calculable, it comes from the infrared. Why would the polynomial pieces just conspire, which are polynomial after all? They don't have these logs, they're not transcendental. Why should those pieces conspire to cancel? Okay, and there's actually a very simple mechanism for doing this. And in fact, it's related to long-known funny tunings that we've seen in quantum field theory. For example, if you open up Paschke and Schroeder, there's a calculation for the lifetime of positronium. So there's a lot of factors that make sense, and then there's this funny factor of pi squared minus 9 that sits in front of it. Now, pi squared minus 9 is a little bit small, but is that an accident? Did it just come out that way? No, there isn't an accident. There's actually a mechanism at work that explains where that pi squared minus 9 comes from and why it appears and why there's a little cancellation. In fact, the mechanism that I'm talking about is well known. It's well known going back to the 1800s. And is a crucial part of proofs of the irrationality of all the numbers that you know and love that are irrational. So let me give an example of how this works by talking about the number log 2. Okay, so log 2 is integral 0 to 1 dx over 1 plus x, and log 2 is transcendental. It's not a rational number, but notice that if you put a different power here other than dx over 1 plus x, it would be rational. So the reason it's transcendental is, the reason it's not rational is exactly that this integrand has a simple pole here at x equals minus 1. Okay, but that tells you something interesting, that if you put some polynomial factor in the integrand, then you're going to get the residue from the residue of the integrand at x equals minus 1. So p of minus 1, you'll get something that multiplies log 2, and everything that does not have a residue will give you something rational. So ahead of time, you know that this integral looks like something times log 2 plus something rational. In other words, it's made out of two different pieces with different number theoretic properties. One of them is transcendental, log 2, the other one is rational. Now let's make a simple choice for this p of x, like x times 1 minus x over 2 to the n. you'll notice this is equal to -1 at x equals -1. So if you just do this integral, on the one hand, it's plus or minus log 2 plus something rational. On the other hand, the left-hand side is tiny because x1 minus x over 2 is bounded by an eighth between 0 and 1. And so that means that if I just hand you the integral, it's totally obvious that it's a tiny number, but any computation of it must split it up into two large pieces, one transcendental and one rational, that have to cancel against each other to high accuracy. So this gives you huge apparent tuning, and in this case, a wonderful rational approximation to log 2. If you take n equals 5, for example, you get this expression for log 2 that's accurate to a part in 100,000. Okay, you can use the same idea for pi, and in fact, it's a good exercise for those of you who like recreational math to use these integrals to actually prove that things like pi, log 2, e, and so on are actually irrational. You give a uniform proof that all of these things are rational. And in fact, this also explains the pi squared minus 9 because the pi squared minus 9 actually is a small phase-space integral. And the integral is manifestly small, but by exactly the same mechanism, it has a rational and a transcendental part that are big, and they have to cancel against each other to high accuracy. So,
hi, Nima, I have you at about 4 minutes. Sorry, okay. I was muted last time.
Okay, sure. No problem. All right. Well, let me just say that you can attempt a similar strategy for the Higgs, and you can actually give some toy examples for it. I don't want to go through these toy examples in. I don't want to go through this toy example in detail, but you can mimic the ideas that we just talked about to give something that's manifestly a tiny potential for the Higgs, but does not manifestly look like a Coleman-Weinberg calculation. However, you can express it as a Coleman-Weinberg calculation, and when you express it as a Coleman-Weinberg calculation, it looks like it has a tree and a loop part, which are miraculously fine-tuned against each other and cancel to exponential accuracy. Okay, so again, that's a toy model, but it's another example to remind us why it's crucial to probe the Euclidean off-shell properties of the Higgs as well as the on-shell ones. All right, if I can I have 5 more minutes, Raman? Okay, great. So let me say.
Sorry. Yes, you can. Yes, you can.
Thank you. Let me say a little bit about this. So the upshot of that first part there is that local quantum field theory makes assumptions about the continuation from Lorentzian to Euclidean. Those assumptions are known to be wrong in gravity. We have examples of where that wrongness sort of shows up on all scales and isn't just restricted to the Planck scale. We know of hidden symmetries and good old-fashioned gauge theories and even simple non-supersymmetric scalar theories. We know that what manifests those hidden symmetries is a representation of ordinary physical observables that does not look obviously local. And so their speculation is that there might be, along those lines, there might be something that represents the physical observables involving the cosmological constant and the Higgs that only appear to be fine-tuned, but that only appear to be fine-tuned when expressed in a form that looks like manifest local quantum field theory, but in their more fundamental form are obviously exponentially small. All right, now I want to talk about a more dynamical idea, the idea of the weak scale as a trigger. And here I want to begin by asking a simple question. What happens in the standard model if we just imagine we took the standard model and we vary m Higgs squared? What changes in the theory as we varied m Higgs squared? What is sensitive to the value of m Higgs squared? What correlation functions care about m Higgs squared? And this seems like a totally stupid question because obviously everything, for example, the spectrum depends on m Higgs squared. But the important point is that the things that care about m Higgs squared are actually correlation functions that are not translationally invariant. They involve more than one space-time point. So there are things like O of x, O of y, or the analog in momentum space. Those things care about m Higgs squared, but the expectation value of local gauge invariant operators do not actually care about m Higgs squared. That's in fact one sort of sharp way of characterizing the hierarchy problem. For example, most dumbly in the standard model, you would say, what about the expectation of h stagger h? doesn't that depend on mh squared? But it doesn't. That's one way of talking about the hierarchy problem. In fact, in the standard model, we don't know how to compute the expectation value of h stagger h. If I try to compute it, then it gets a contribution from closing the loop that has the usual dependence on the cutoff square. And it's true for almost all the other local operators. For example, what about the expectation value of the local operator that's a Yukawa coupling? Well, the Yukawa couplings, actually Yukawa couplings break all the chiral symmetries, and so I can close this loop up with Yukawa coupling and get another power sensitive contribution to this guy. Said another way, if I say it slightly more physically, if we imagine very weakly coupling the standard model to some spectator fields, let's say very weakly coupling h stagger h to some field phi, the problem is that I can't actually compute the potential for phi. If I write down epsilon phi h stagger h, it has all the same symmetries as epsilon phi times some high scale squared. And so really we'd say there's a linear term for phi that we can't compute, and we have to take from experiment. Okay, so there's one famous exception to this, which is the anomaly. If we look at the expectation value of glue-glue dual, the anomaly, the whole point is that naively this is zero, it's a total derivative. But in fact, because of the anomaly, it's not zero, and it's lambda QCD cubed actually times m up. And so the expectation value of glue-glue dual does sensitively depend on the Higgs mass squared. We can say that glue-glue dual is triggered by the weak scale. And so it's true, the expectation value of glue-glue dual changes dramatically, whether m Higgs squared is positive or negative, or the value depends sensitively on what m Higgs squared is. And so this triggering is used cosmologically in relaxion models as an approach to the hierarchy problem. But I want to take this idea of triggering and think about it slightly more generally. Now, are there other triggers? No in the standard model. But it's possible to have other triggers beyond the standard model, and a very simple possibility is in 2x doublet extensions of the standard model. So, for instance, say we have a 2x doublet model to begin with an exact Peche-Quinn symmetry, just classically. And we imagine that HUHD is charged under the Peche-Quinn. Now, this is very important because it means that the expectation value of HUHD is a trigger. It's potentially a trigger. There is no UV contribution to the expectation value of HUHD because of the PQ symmetry. I can't close this. I can't close that loop, or more invariantly because of the PQ symmetry. So let's just ask in this theory, just trivially, classically, as I vary mh up squared and mh down squared, what do I get for the expectation value of h up, h down? And the answer is it's zero everywhere, except when both Higgs mass squareds are negative. So in order for HUHD to trigger, we have to have that both mh up squared and mh down squared are negative. And then if we do, then HUHD turns on. So HUHD is another example of a trigger. Now, QCD also breaks these symmetries. So in more detail in these other regions, we can also get very small expectation values that are suppressed by powers of the QCD scale over higher scales. So I'm going to ignore that now. We'll talk about it in more detail in what we're going to write. But the basic point is that in a 2x doublet model, there is a trigger. There is something that's triggered by the weak scale. However, it's crucial for this mechanism, for this triggering to work. It's crucial that there is no B term. Of course, we know we have to break the Peche-Quinn symmetry, otherwise we'd have a weak scale axion. And conventionally, the easiest way to do that is by a B term. But that would destroy the trigger mechanism because the expectation value of HUHD would just be set by B. They have the same quantum numbers and would be totally independent of MH up squared and MH down squared. But that's fine. The trigger-happy version of this idea is to break the Peche-Quinn symmetry only with a quartic coupling that has charge 2. So we set B and everything else to 0. That means that HUHD is now totally calculable. Can't be generated by this breaking of PQ symmetry. And on the other hand, we again need both MH up squared and MH down squared to be negative to trigger. So this is the model we're talking about. It's just a 2x doublet model, but in a limit where we turn off everything that breaks a Peche-Quinn with charge 1 and only keep this quartic coupling that breaks a Peche-Quinn with charge 2. And you'll notice that, again, for things to trigger, both the Higgs mass squareds have to be negative. We can't make these quartics too big for the usual reasons of Landau poles and so on. And so this is a model where all the states are necessarily light. There's no decoupling limit. Okay? It's impossible to decouple. We have to have both the Higgs mass squareds negative. Phenomenologically, just in order not to be dead, we have to have that V down over V up is less than around 0.3, and that makes everybody light. The sort of second Higgs associated with the H down, for example, is lighter than 100 GeV. Everyone else is lighter than, maybe 150, 200 GeV at most. So naively, you would think this is dead, but at least we've been looking systematically, and it seems large parts of this very constrained parameter space are alive. They're alive from left, they're alive from the LHC, and in fact, the regions that are alive, we might get 3 sigma evidence eventually from the LHC, but it won't hit us over the head. On the other hand, there will be huge signals at a Higgs factor. And I won't explain how we use this trigger. There are various ways you might imagine to use this trigger in order to exploit why both Higgs masses have got to be tuned down in the neighborhood of the weak scale. I'm out of time, so I'll just mention that the idea that we've been exploring, there are perhaps others, is to imagine that the coupling of H up, H down to a bunch of scalar fields in a sort of concrete model of the landscape could be crucial in order to fine-tune the cosmological constant to be small enough to satisfy Weinberg's bound. So there's a way of correlating the cosmological constant and hierarchy problems with this kind of idea. That involves other experimental signals, lots of light scalars that can also give you long-range forces and dark matter. But anyway, I don't have time to talk about that in detail. The crucial point, if I just come back, the crucial point is in this second idea. I think the most interesting point is that in order to have this other way of having the weak scale as a trigger, you unavoidably have light states in this 2-exoublet model. There's no decoupling limit. They absolutely must be visible. In fact, it's surprising, to me, it's shocking that something like this is not yet ruled out. But it's not ruled out, and as far as we can tell, it's not ruled out. It's a good target for the rest of the LHC. It's a qualitative target for the rest of the LHC to see if we can actually tell whether there's evidence for triggering of the weak scale along these lines. And in any case, it's a spectacular target for future Higgs factor. All right, thank you very much. Sorry for going so long over.
Okay, thank you. So I wanted to take some questions here. One was what's so special about gravity that leads to UV-IR mixing? Can't you engineer a microscopic condensed matter Hamiltonian with the same properties? And in particular, where does the analytic continuation fail?
Well, so what's special about gravity is that only gravity has this feature of universally coupling to energy, so that when you go to high enough energy, you make a big black hole instead of probing shorter and shorter distances. Now a bunch of things fail in the condensed matter analog. Literally, the condensed matter analog isn't even Lorentz invariant. So I mean, let me make the point not formal but kind of vivid. Okay, let's say you had a condensed matter system. You have a bunch of phonons. You scatter the phonons at high energies. You go to higher and higher energies. You eventually see that the underlying degrees of freedom are nothing like phonons. They're the atoms and molecules and all the rest of it. So in a sense, it's much more dramatic. The low energy degrees of freedom are totally gone by the time you go to high energy. That is amazingly not true in gravity. And in fact, in a sense, the ultraviolet completion of gravity, it's much easier to make predictions from it than about, for example, the weak interactions before we knew about the W and the Z. That's a big irony. Ahead of time, we know what happens when we collide particles at 1,000,000 M Planck. You make a large black hole. And what does a large black hole do? It Hawking evaporates with low energy Hawking radiation. So that's kind of amazing. We know ahead of time what happens when you do grossly. There's details about how the information comes out, blah, blah, blah. But grossly, we know what happens. You make a big black hole and it Hawking evaporates into what? The same low energy degrees of freedom that went in to produce it to begin with. So it's very, very different than in condensed matter systems, or even in some field theory systems, where you want to know about higher and higher, shorter and shorter distances. You just go there with higher and higher energies. There's an obstruction to a gravity. It has everything to do with black holes and horizons. This is sort of codified in the fact that local quantum field theory has power law behavior for correlation functions, whereas gravity does not. Well, first, we don't even have a well-defined notion of local correlation functions, but even when we talk about things like scattering amplitudes, high energy scattering amplitudes in gravity are exponentially soft. We never get that exponential softness, let's say 2 to 2 scattering. We don't get exponential softness of that sort in field theory.
Got it. Alexandra Alves asks, do you think some kind of entropic principle could play a role in solving the hierarchy problem? Something like the causal entropic principle proposed some years ago to explain the CC?
Well, I think if I understand what you mean, those are things that have to do with trying to make sense of some kind of notion of a measure on the landscape. And I'm very sympathetic to the rough idea that there might be something like a landscape. There's lots of not just these huge clues like the cosmological constant, lots of little circumstantial things, funny accidents in the pattern of coupling constants in the standard model. But my own feeling is that it's a cartoon, that there's sort of good evidence that there may be gazillions of metastable vacua in some underlying theory. If that's true, it's trivial to arrange that in simple models of the sort that I was actually alluding to earlier. You just take, 100 scalar fields with 2 minima each, you have 2 to the 100 vacua. But the fact you get exponentially large number of vacua is not a big deal, or even particularly hard to imagine. So parts of the story are solid, but all the parts that have to do with trying to understand how to populate these vacua cosmologically are a morass. And of course, there have been various proposals for trying to make sense of this morass, but I think even the people making them would agree none of them are really fully satisfactory. So my own feeling is that the cosmological part of the landscape story is like a cartoon for something that might be true in some vague sense, but it's mostly an inspiration to think about a very hard problem. And my feeling is that we're not close to having the right sort of grammar yet to correctly pose the question. I think it's maybe one of the deepest, hardest problems in physics, but I don't think we're particularly close. So I don't think that proposal or any of the other proposals for making sense of the measure are really bringing us much closer to understanding what's going on.
Okay, very good. So one thing that maybe you can do once you're off here is Ite Block was just asking if you can send a link for the 4 hours of the talk that you would give if it's something public.
Yeah.
Maybe you could do that after we finish. And